6 galaxies appeared on James Webb's sensors that shouldn't exist. Not according to our best theories, not according to decades of cosmological modeling. These galaxies formed when the universe was barely 500 million years old, yet they're almost as massive as the Milky Way, packed with hundreds of billions of stars that had no business being there. The James Webb Space Telescope launched with a mission to peer deeper into cosmic history than any instrument before it. What it found in those first deep field images wasn't just unexpected, it was impossible. Picture the early universe as a construction site. You've got raw materials, hydrogen and helium, scattered everywhere. Dark matter is slowly clumping together, creating gravitational wells that should gradually pull normal matter into small protogalaxies. These fragments should then merge over billions of years, building larger structures piece by piece. That's the script. That's what the Lambda-CDM model, our standard cosmological framework, predicts with mathematical precision. If you find comfort in these gentle explorations of space and science, I'd be grateful if you'd consider subscribing and giving this video a like. Webb looked at that construction site and found skyscrapers already standing. An international team analyzing Webb's early observations identified 6 candidate galaxies existing roughly 500 to 700 million years after the Big Bang. More than 13 billion years ago, when the universe was only 3% of its current age. The problem? These reddish dots in Webb's images appeared 50 times more massive than our models said they could be. Let's put that timeline in perspective. The Milky Way forms about 2 new stars per year, slow and steady. For these 6 galaxies to reach the masses Webb detected, they would need to birth hundreds of new stars annually for hundreds of millions of years, starting almost immediately after the Big Bang. That's not just fast. It's operating at the theoretical edge of physical possibility. Star formation has efficiency limits. Typically, only about 10% of available gas converts into stars. The rest gets blown away by stellar winds, supernovae, and radiation pressure. It's a messy, wasteful process. But the data from these early galaxies suggested something different. Something that made astronomers physically uncomfortable when they ran the numbers. These galaxies appeared to be converting nearly 100% of their available gas into stars. You can't just dial up star formation to maximum efficiency because you need it. Physics doesn't work that way. Gas needs to cool. Clouds need to collapse. Gravity needs time to do its work against the outward pressure of heat and radiation. The early universe was hotter, more energetic, more chaotic. Conditions should have been worse for star formation, not better. Yet there they were, 6 impossible galaxies staring back at us from the cosmic dawn. The immediate reaction from the astronomical community wasn't celebration. It was doubt. When observations contradict well-established theory, the first assumption is that you're measuring something wrong. Maybe these aren't galaxies at all. Maybe they're something else masquerading as early galaxies. Maybe the mass estimates are wildly off. That's where spectroscopy comes in. Webb's initial observations used imaging, capturing light across different wavelengths to estimate distances and masses. But imaging gives you educated guesses. Spectroscopy gives you certainty. It splits light into its component wavelengths, revealing the precise chemical fingerprints of what you're observing. Temperature, composition, velocity, mass, all encoded in those spectral lines. The 6 galaxies needed spectroscopic confirmation. And while astronomers waited for that data, they started proposing explanations. The first theory involved supermassive black holes. If these galaxies hosted active black holes at their centers, the intense radiation from matter spiraling into those black holes could make the galaxies appear much brighter and therefore more massive than they actually are. It's a plausible explanation. We know supermassive black holes existed surprisingly early in cosmic history. Maybe we're not seeing huge stellar populations, but rather compact, brilliant black holes fooling our mass estimates. But that explanation had problems of its own. How do you form supermassive black holes that quickly? Black holes need seed masses. They need time to grow by consuming surrounding matter. Getting them to millions or billions of solar masses in the first few 100 million years requires its own set of impossibilities. The second major explanation involved what researchers called bursty star formation. Standard models assume star formation proceeds relatively smoothly over time. But what if the early universe worked differently? Computer simulations suggested a possible mechanism. Young stars form by pulling in surrounding gas. When those massive stars die in supernova explosions, they blast gas back out into space. This creates a rhythm, a cosmic heartbeat. Gas flows in, stars form, supernovae erupt. Gas gets expelled. Things calm down. Then the cycle repeats. In the early universe, with its different conditions, these bursts might have been far more dramatic than anything we see today. If Webb happened to catch these galaxies during their burst phases, when hundreds of stars were forming simultaneously, they would appear incredibly bright. Not because they contain as many total stars as the Milky Way, but because we're seeing them during a temporary fireworks display. As astronomers waited for spectroscopic data, more discoveries kept piling up. Webb found 3 galaxies with stellar masses comparable to the Milky Way, forming stars nearly twice as efficiently as their lower mass neighbors. Their high dust content gave them a distinctive red appearance in Webb's images. Astronomers dubbed them the Red Monsters. These galaxies didn't necessarily contradict the standard cosmological model, but they raised uncomfortable questions about galaxy formation processes we thought we understood. Then came JADES-GS-Z 13-1. This galaxy appeared 330 million years after the Big Bang, with a redshift of 13.05. By itself, that's remarkable, but not paradigm-shattering. What made astronomers stop in their tracks was the light coming from this galaxy, specifically an emission line called Lyman alpha. Lyman alpha is ultraviolet light emitted by hydrogen atoms when their electrons drop from an excited state to the ground state. It's one of the brightest spectral signatures in the universe. But in the early universe, Lyman alpha light shouldn't be visible at all. Here's why. After the Big Bang, the universe was ionized, a hot plasma where electrons roamed free from atomic nuclei. As the universe expanded and cooled, those electrons combined with protons to form neutral hydrogen atoms. This happened about 380,000 years after the Big Bang, during an event called recombination. For the next several 100 million years, the universe was dark, filled with neutral hydrogen gas that absorbed ultraviolet light like Lyman alpha. This period is literally called the Dark Ages. Eventually, the first stars and galaxies formed, and their intense radiation began reionizing the neutral hydrogen, clearing the fog and making the universe transparent again. This reionization process took time. Standard models suggested it completed about 1 billion years after the Big Bang. The Lyman alpha emission line had never been detected earlier than 550 million years after the Big Bang. JADE's GS-Z13-1 showed bright Lyman alpha emission at 330 million years. That's like finding a radio signal from a submarine deep underwater. The signal shouldn't make it through. The neutral hydrogen fog should have absorbed those photons completely. Yet there it was, clear as day, suggesting either this galaxy somehow cleared its own bubble of ionized space far earlier than models predicted, or reionization started much earlier and proceeded very differently than we thought. The implications stretch beyond just galaxy formation. They touch the fundamental timeline of cosmic evolution. Meanwhile, spectroscopic follow-up on some of the original 6 candidate galaxies started coming back, and the picture got complicated. Some of those galaxies were exactly what they appeared to be: massive, early, and deeply problematic for standard theory. Others turned out to be less massive than initial estimates suggested. The black hole hypothesis proved correct for several. These weren't normal galaxies, but what astronomers started calling little red dots, compact objects dominated by supermassive black holes rather than stellar populations. But even after accounting for misidentifications, even after removing the black hole imposters, there were still roughly twice as many massive galaxies in Webb's early universe data as the standard model predicted. That's when the real debate began. The Lambda-CDM model has been the reigning paradigm in cosmology since the late 1990s. Lambda represents dark energy, the mysterious force accelerating the universe's expansion. CDM stands for cold dark matter, the invisible gravitational scaffolding that provides the framework for galaxy formation. This model explains the cosmic microwave background radiation, the large-scale structure of galaxy distribution, the abundances of light elements, and the universe's accelerating expansion. It's passed every major observational test for decades, but it makes specific predictions about how galaxies form. In Lambda-CDM, dark matter clumps together first under gravity, creating potential wells. Normal matter falls into these wells, cools, and eventually forms stars and galaxies. This is a gradual process. Small structures form first, then merge into larger ones over cosmic time. By 500 million years after the Big Bang, you should see lots of small protogalactic fragments that haven't yet assembled into massive galaxies. Webb saw fully formed behemoths. The question became, is this a crisis for Lambda-CDM, or just a wrinkle that needs smoothing? Some astronomers argued for crisis. If the galaxy masses and ages are confirmed, they said, we need fundamental changes to cosmological theory. Maybe the universe expanded faster immediately after the Big Bang than current models predict. Maybe dark matter behaves differently than we thought. Maybe entirely new forces or particles are involved. Others urged caution. Cosmology has a long history of apparent contradictions that resolved with better data and refined understanding. The standard model has survived challenges before. This might just require tweaking our understanding of star formation efficiency in the early universe, not abandoning the entire framework. As months passed and more data accumulated, a nuanced picture emerged. The Lambda-CDM model itself wasn't broken. The fundamental cosmology, the expansion rate, the dark matter framework, the timeline of the Big Bang, all still held up under scrutiny. What needed revision was our understanding of the astrophysical processes occurring within that cosmological framework. Star formation in the early universe was clearly more efficient than models predicted. The bursty formation hypothesis gained support from detailed simulations. When researchers modeled these rapid cycles of gas inflow, star formation, and supernova-driven outflow, they could reproduce galaxies that appeared extremely bright during burst phases without requiring impossible total stellar masses. The turbulent nature of early galaxies provided another piece of the puzzle. Webb captured detailed observations of more than 250 young galaxies existing between 800 million and 1.5 billion years after the Big Bang. Analysis of gas movements within these galaxies revealed chaotic, clumpy systems that hadn't settled into the smooth rotating disks we see in mature galaxies like the Milky Way. This turbulence actually helps explain rapid star formation. In a calm, rotating disk, gas orbits at different speeds depending on distance from the center. This differential rotation makes it hard for gas clouds to collapse and form stars. But in a turbulent, chaotic environment, gas clumps collide and merge much more readily. Gravitational instabilities grow faster. Stars form in dramatic bursts rather than steady trickles. As the universe aged and galaxies grew larger, their gravity strengthened. Eventually, it became too strong for supernova explosions to expel gas effectively. The bursty cycle slowed down, transitioning to the more sedate star formation we observe in present-day galaxies. But in those early chaotic times, the universe was a far wilder place than our steady-state models anticipated. Then, Webb found the Milky Way's cousins. Peering back 9 to 13 billion years, Webb identified over 1,000 disk galaxies resembling our own Milky Way structure. Out of nearly 4,000 galaxies observed, more than 1,600 showed the distinctive disk morphology. These galaxies existed when the universe was just a few billion years old, during an era when astronomers expected the cramped conditions and frequent collisions to twist any orderly structures into irregular blobs. The discovery suggested either disk galaxies are more robust than theory predicted, or the early universe was less violent in certain regions than models assumed. Either way, it hinted that our understanding of galactic evolution contained significant gaps. Galaxy JWST 7329 pushed those gaps even wider. This galaxy appeared as it was 11.5 billion years ago, just 2 billion years after the Big Bang. At that tender cosmic age, it already contained a stellar population around 1.5 billion years old. Stars that must have formed when the universe itself was barely 500 million years old. The galaxy boasted 4 times as many stars as the present-day Milky Way. More remarkably, JWST 7329 appeared to be quenched. It had stopped forming stars at least 1 billion years before Webb observed it. Quenching requires a galaxy to lose or heat its cold gas supply, shutting down the star formation process. In the local universe, we see quenched galaxies all the time. But finding one so massive, so mature, and so dead at such an early epoch challenged everything astronomers thought about how quickly galaxies could evolve through their life cycles. What mechanism could quench a galaxy that early? Supermassive black hole feedback, environmental effects, something else entirely. The questions kept multiplying faster than the answers. In early 2025, Webb discovered what astronomers nicknamed the Big Wheel, a massive galaxy with pronounced spiral structure existing within the first 2 billion years of the universe. You'd expect such an early massive galaxy to be elliptical, with a smooth, featureless appearance resulting from chaotic formation processes. Instead, the big wheel showed elegant spiral arms similar to much later galaxies, including our own Milky Way. Spiral structures require specific conditions. The galaxy needs to be rotating in an organized way. It needs to be relatively isolated, not undergoing major mergers that would scramble its structure. It needs time for density waves to develop and propagate through the disk, creating the spiral pattern. Finding all these conditions met so early in cosmic history was yet another surprise from an instrument that seemed determined to upend expectations at every turn. The record-breaking distances kept falling. Astronomers confirmed a galaxy designated MOM-Z14 with a cosmological redshift of 14.44. Its light traveled through expanding space for approximately 13.5 billion years, meaning we're seeing this galaxy as it existed just 300 million years after the Big Bang. And like many of its early peers, MOM-Z14 appeared roughly 100 times brighter than theoretical predictions. These aren't subtle discrepancies. These are order of magnitude differences between observation and theory. As spectroscopic data accumulated and analyses grew more sophisticated, astronomers began separating the truly anomalous galaxies from the misidentified objects. The population of problematic early galaxies decreased from the initial shocking numbers, but it didn't disappear. A solid core of genuine mysteries remained, galaxies that really are too massive, too mature, or too structured for their cosmic age. The search for population 3 stars added another layer to the investigation. These hypothetical first-generation stars would have formed from primordial gas containing virtually no elements heavier than helium. With different chemical composition, they should have been far more massive than modern stars, burning brilliantly and dying young. Their unique spectral signatures might be detectable by Webb, hidden within the light from the earliest galaxies. Finding population 3 stars would open a window into the universe's first few 100 million years, the era before enough supernovae had occurred to enrich the cosmos with heavy elements. It would reveal the conditions under which the first galaxies assembled. But detecting these ancient stellar populations requires pushing Webb's capabilities to their absolute limits, separating faint chemical signatures from the overwhelming light of later generation stars. The implications extend beyond pure astronomy. Our existence in a disk galaxy like the Milky Way suggests these structures might provide particularly favorable conditions for life. If disk galaxies existed far earlier than expected, and if they indeed offer better conditions for planet formation and biological evolution, then life might have emerged much earlier in cosmic history than most scientists assumed. Somewhere out there could be civilizations billions of years older than humanity, arising in galaxies that formed when the universe was still in its infancy. But we're getting ahead of ourselves. Before we can speculate about ancient alien civilizations, we need to understand what Webb is actually showing us. We need to reconcile these observations with physical theory. We need to figure out whether we're seeing a revolution in cosmology or simply a revolution in our understanding of astrophysical processes within a fundamentally correct cosmological framework. The data suggests the latter. The standard model isn't broken, but it's clearly incomplete. What we're witnessing isn't the death of Lambda-CDM cosmology. It's the birth pains of a more sophisticated understanding of how galaxies actually form and evolve. The framework, dark matter, dark energy, the expanding universe, the Big Bang timeline, all remains intact. What's changing is our grasp of the messy, complex, wildly variable processes that transform dark matter halos and primordial gas into the magnificent structures we call galaxies. And that brings us to the heart of the mystery. Because understanding what's happening requires us to journey back to those first few 100 million years after the Big Bang. We need to explore the Dark Ages, the epoch of Reionization, the formation of the first stars. We need to understand not just what Webb is seeing, but what the early universe actually was. A place far stranger and more dynamic than our comfortable models ever imagined. The universe, 300 million years after the Big Bang, was not supposed to be interesting. At least not in the way Webb revealed it to be. According to every model, every simulation, every theoretical framework we'd constructed, this epoch should have been dominated by small protogalaxies, messy clumps of gas and dark matter just beginning their slow gravitational collapse. The universe was supposed to be building itself from the bottom up, assembling complexity piece by piece over hundreds of millions of years. What we found instead was organization appearing with shocking rapidity. JADES-GS-Z13-1 represents perhaps the most confounding example of this premature sophistication. This galaxy exists at a redshift of 13.05, meaning we observe it as it was just 330 million years after the Big Bang. That alone wouldn't be particularly remarkable. We've found galaxies nearly that old before. What makes JADES GS-Z13-1 extraordinary is what it's doing. It's emitting Lyman alpha radiation. You're probably wondering why that matters. Here's the thing about Lyman alpha emission. It's a specific wavelength of ultraviolet light produced when electrons in hydrogen atoms drop from an excited state to their ground state. In the modern universe, we see this emission all the time. It's a common spectral signature from regions of active star formation. But the early universe was fundamentally different from the cosmos we inhabit today. Between roughly 380,000 years after the Big Bang and about 1 billion years later, the universe went through a phase astronomers call the Dark Ages. During this period, neutral hydrogen gas filled all of space like a thick fog. Any Lyman alpha photons emitted by early stars or galaxies would be immediately absorbed by this neutral hydrogen, scattered and rescattered until their signal became undetectable. The universe was opaque to this particular wavelength of light. This fog only lifted through a process called reionization. As the first stars and galaxies formed, their intense radiation gradually ionized the surrounding hydrogen, stripping electrons from their atoms. This created expanding bubbles of ionized gas around each luminous object. Over hundreds of millions of years, these bubbles grew and merged until the entire universe had been ionized. Only then could Lyman alpha radiation travel freely through space. Based on observations of quasars and other distant objects, astronomers had determined that reionization was essentially complete by about 1 billion years after the Big Bang. Prior to that, we'd never detected Lyman alpha emission from any galaxy earlier than 550 million years after the Big Bang. The neutral hydrogen fog should have been too thick, too pervasive to allow such signals through. JADES GS-Z13-1 exists 220 million years before that supposed limit. The galaxy is broadcasting a clear, strong Lyman alpha signal from an era when the universe should have been shrouded in neutral hydrogen. It's like receiving a radio transmission from inside a Faraday cage. The signal simply shouldn't be able to escape. Either our understanding of when and how reionization occurred is wrong, or something unusual is happening in the immediate vicinity of this galaxy. Perhaps it sits in an enormous bubble of ionized gas, carved out by an unusually intense burst of star formation. Perhaps reionization didn't proceed uniformly throughout the universe as we'd assumed, but instead occurred in complex, patchy patterns, with some regions clearing much earlier than others. Perhaps the physics of how Lyman alpha photons interact with neutral hydrogen is more subtle than our models account for. Each possibility opens new questions. If reionization began earlier or proceeded differently than we thought, it suggests the first stars formed sooner and in greater numbers than our models predict. That would require revising our understanding of how gas clouds collapsed in the early universe, how dark matter halos assembled, how stellar feedback regulated subsequent star formation. The implications cascade through our entire picture of cosmic dawn, but JADES-GS-Z13-1 is just one example of early galaxies behaving in unexpected ways. The broader pattern emerging from Webb's observations suggests the first few 100 million years after the Big Bang were far more eventful than anyone anticipated. Consider the turbulence. When astronomers analyze the internal structure of more than 250 galaxies from 800 million to 1.5 billion years after the Big Bang, they discovered these weren't the orderly rotating disks we see in the modern universe. They were chaotic, clumpy systems, clouds of gas and stars swirling in irregular patterns, with massive star-forming regions appearing and disappearing on timescales of mere millions of years. This turbulence makes sense from a theoretical perspective. In the early universe, galaxies were smaller and less massive. Their gravitational wells were shallower. When massive stars exploded as supernova, they could blow significant amounts of gas out of the galaxy entirely. This created a kind of cosmic breathing, gas falling in to form stars, then being expelled by stellar feedback, then falling back in to form another generation of stars. Modern galaxies don't behave this way. They're too massive. Their gravity is too strong. When stars explode, the ejected gas doesn't escape. It just redistributes within the galaxy. Star formation proceeds at a steadier, more regulated pace. But in the early universe, this breathing mechanism allowed for what researchers call bursty star formation. Here's where things get interesting for our impossible galaxies. If star formation occurred in intense bursts rather than as a steady process, then timing matters enormously. When we observe a distant galaxy, we're seeing it at one specific moment in its history. If we happen to catch it during a burst phase, when it's converting gas to stars at 10 or 100 times its average rate, it will appear far more luminous than its total stellar mass would suggest. Imagine trying to estimate someone's wealth by measuring how much money they're spending at a particular moment. If you catch them during a normal day, you might get a reasonable estimate. But if you observe them during an unusually expensive purchase, buying a house or a car, you'll vastly overestimate their total assets. You're seeing a temporary spike in activity, not the steady state. The same principle applies to bursty galaxies. Their brightness during star formation bursts doesn't reflect their total stellar mass. It reflects the temporary intensity of their current star-making episode. When astronomers initially estimated the masses of those 6 impossible early galaxies, they were essentially catching them mid-burst, and extrapolating from that snapshot to their entire stellar population. Supercomputer simulations of galaxy formation that incorporate this bursty behavior produce results that match Webb's observations far better than steady-state models. The galaxies appear brighter than expected, not because they contain impossibly large numbers of stars, but because we're witnessing the fireworks of intense star formation bursts, temporary episodes of brilliance in galaxies that are actually much more modest in their total stellar mass. But that's not the complete explanation, because some of those bright early objects aren't galaxies at all. Enter the little red dots. When astronomers began spectroscopic follow-up observations of some of the brightest early galaxies, they discovered something unexpected. The spectra didn't match what you'd expect from stellar populations. Instead, they showed signatures characteristic of active galactic nuclei, supermassive black holes actively consuming matter. These objects appear as small reddish points in Webb's images, hence the informal name. But they're not ordinary galaxies hosting black holes. They seem to be dominated by their central black holes to an unusual degree. The black hole's mass may represent a significant fraction of the total mass of the system, far higher than the ratio we observe in modern galaxies, where the central black hole typically comprises less than 1% of the galaxy's total mass. This presents its own mystery. How did supermassive black holes grow so large so quickly? In the modern universe, black holes grow by accreting matter from their surroundings. But this process has natural speed limits. There's only so fast a black hole can consume gas before the radiation from that infalling matter becomes so intense, it blows away the remaining fuel. Growing a billion solar mass black hole through this standard process should take longer than the age of the universe at these early epochs. Either the first black holes formed through some unusual mechanism, perhaps from the direct collapse of massive gas clouds rather than from stellar remnants, or they grew faster than our models suggest is possible. Perhaps the physics of accretion works differently in the dense environment of the early universe. Perhaps these black holes underwent periods of super-Eddington accretion, consuming matter faster than should theoretically be stable. What we're witnessing is the universe in its wild youth, before the laws and patterns that govern modern cosmic evolution had fully established themselves. The early universe wasn't just smaller and denser. It operated under different conditions that allowed for phenomena we simply don't see today. Stars form differently. The very first generation, population 3 stars, formed from pristine gas containing essentially no elements heavier than helium. Without metals to facilitate cooling, these gas clouds had to be much more massive before they could collapse. Population 3 stars might have been dozens or even hundreds of times more massive than the Sun, burning brilliantly for just a few million years before exploding as supernovae or collapsing directly into black holes. We haven't definitively detected population 3 stars yet. Their spectral signatures are subtle, easily lost in the light from later generation stars. But Webb's instruments might be sensitive enough to pick out these signatures if we know where to look. Finding confirmed population 3 stars would open a window into the universe's first few 100 million years, the era before stellar nucleosynthesis had enriched the cosmos with heavy elements. The discovery of over 1,600 disk galaxies in the early universe adds yet another dimension to this emerging picture. For decades, astronomers assumed that disk galaxies like the Milky Way were fragile structures that couldn't form or survive in the chaotic early universe. Galaxy collisions were more frequent. The universe was more crowded. Any ordered rotation should have been disrupted by gravitational interactions. Yet there they are, spiral galaxies with well-defined disks existing when the universe was just a few billion years old. The Big Wheel galaxy takes this even further, displaying clear spiral structure within the first 2 billion years after the Big Bang. You'd expect such a massive early galaxy to be elliptical, a smooth blob of stars formed from the merger of smaller galaxies. Instead, it shows the delicate spiral arms characteristic of a rotating disk that's avoided major mergers. This suggests galaxy evolution followed multiple paths even in the early universe. Some galaxies grew through mergers, building themselves up from smaller pieces and ending up as elliptical systems. Others somehow assembled more quietly, maintaining coherent rotation as they accumulated mass. The conditions that determined which path a galaxy followed remain unclear. What's becoming clear is that the universe between 300 million and 1 billion years after the Big Bang was far more diverse and complex than our model suggested. It wasn't simply a scaled-down version of the modern cosmos. It was a fundamentally different place where processes we barely understand today dominated cosmic evolution. The question now is whether we can develop a coherent framework that explains all these observations: the bright early galaxies, the turbulent star formation, the early Reionization, the supermassive black holes, the unexpected disk structures, without abandoning the Lambda-CDM model that successfully explains so many other aspects of cosmic history. That framework is beginning to emerge piece by piece as theorists work to incorporate the new observations into refined models of the early universe. One mechanism gaining traction centers on something cosmologists call bursty star formation, a process that sounds almost organic, like a cosmic heartbeat pulsing through the early universe. Instead of forming stars at a steady, predictable rate, these early galaxies might have experienced dramatic cycles. Gas would rush inward under gravity's pull, condensing into stars at prodigious rates. Then, those massive stars would explode as supernovae, blasting gas back out into space. The galaxy would go dark for millions of years, while gravity slowly gathered that expelled material back together. Then the cycle would repeat. Another burst of intense star formation, another wave of supernova, another period of dormancy. This rhythmic pattern changes everything about how we interpret brightness. When Webb looks at a distant galaxy, it captures a single moment in that galaxy's history. If that moment happens to coincide with a burst phase, the galaxy appears extraordinarily luminous, packed with young, hot stars pumping out ultraviolet radiation. A few million years earlier or later, that same galaxy might have looked far dimmer, its stars having burned out and no new ones yet forming. Researchers ran supercomputer simulations incorporating this bursty behavior, feeding in the physics of gas dynamics, stellar evolution, and supernova feedback. The results matched observations remarkably well. Galaxies in the simulation appeared bright enough during burst phases to account for what Webb sees, yet their total stellar masses remained within plausible limits. The problem wasn't that these galaxies contained impossibly many stars. It was that we happened to catch them during their brief moments of intense activity. But this explanation only works if the early universe supported such extreme cycles. In today's massive galaxies, gravity holds expelled gas so tightly that supernovae can't effectively clear it away. Star formation proceeds more steadily because there's always gas available. Yet in the smaller, lower mass systems common in the early universe, gravity's grip was weaker. Supernova explosions could temporarily empty these protogalaxies of gas, creating the pauses necessary for bursty behavior. The timeline matters here. As the universe aged and these small galaxies merged into larger structures, their increasing mass would have dampened the burstiness. Gravity grew strong enough to retain gas despite supernovae. Star formation transitioned from violent pulses to the more sedate, continuous process we observe in modern galaxies. This shift might have occurred around 1 billion years after the Big Bang, right around the time when Webb's observations start matching traditional predictions more closely. Then there's the black hole factor. Not all of those bright early objects turned out to be galaxies packed with stars. Some revealed themselves to be little red dots, compact sources that don't quite fit any existing category. Their spectra show characteristics of both galaxies and active galactic nuclei, suggesting there's something intermediate. Perhaps young supermassive black holes surrounded by dense stellar populations, or perhaps the earliest quasars in a formation stage we've never observed before. Black holes solve the brightness problem in a fundamentally different way than bursty star formation. When matter spirals into a black hole, friction in the accretion disk heats material to millions of degrees. This superheated gas radiates intensely across the electromagnetic spectrum. A relatively modest black hole, perhaps a few million times the Sun's mass, can outshine an entire galaxy of stars if it's actively feeding. The challenge is explaining how supermassive black holes grew so large so quickly. Standard theory holds that black holes grow gradually, accumulating mass over hundreds of millions of years. Yet Webb detects black holes exceeding 1 billion solar masses when the universe was less than 700 million years old. Something accelerated their growth far beyond normal rates. One possibility involves the direct collapse of massive gas clouds in the early universe. Instead of forming stars first, and then having those stars collapse into stellar mass black holes that slowly merge and accumulate matter, perhaps some pristine gas clouds collapse directly into massive seed black holes weighing tens of thousands of solar masses. These seeds would have a significant head start, potentially reaching supermassive status much faster than black holes that began as individual stars. Another mechanism focuses on super-Eddington accretion, black holes consuming matter faster than theoretical limits normally allow. The Eddington limit describes the maximum rate at which a black hole can accrete material before radiation pressure from the accretion disk blows away incoming gas. But if gas arrives from multiple directions simultaneously, or if the accretion disk has unusual properties in the early universe's metal-poor environment, perhaps black holes could temporarily exceed this limit and grow at accelerated rates. Distinguishing between star-dominated galaxies and black hole-dominated systems requires spectroscopy, splitting light into its component wavelengths and analyzing the detailed patterns. Initial observations of many Webb discoveries relied on photometry, measuring brightness in several broad wavelength bands. This gives rough estimates of distance and mass, but can't definitively separate stellar light from black hole emission. Follow-up spectroscopic observations have been slowly clarifying the picture. Some objects initially thought to be impossibly massive galaxies turned out to host luminous black holes that inflated their apparent brightness. Others, however, showed spectral signatures consistent with stellar populations, confirming they really are galaxies with extraordinary star formation rates or caught during burst phases. The galaxy JWST 7329 represents a particularly puzzling case. Located 11.5 billion light-years away, we see it as it appeared just 2 billion years after the Big Bang. Yet its stellar population appears to be 1.5 billion years old, meaning star formation began when the universe was merely 500 million years old. This galaxy contains 4 times the Milky Way's stellar mass, but shows no signs of ongoing star formation. It's quenched, having somehow exhausted or expelled its gas supply. Quenching usually happens to galaxies much later in cosmic history, typically through processes like active galactic nucleus feedback, where a central black hole's energy output heats and disperses gas, or ram pressure stripping, when a galaxy moves through intergalactic gas, which strips away its star-forming material. Yet JWST 7329 underwent quenching extraordinarily early. Either feedback mechanisms were far more efficient in the early universe, or we're missing some fundamental process that could shut down star formation in young galaxies. The 3 red monsters add another dimension to this puzzle. These massive galaxies, observed when the universe was between 1 and 2 billion years old, show stellar masses comparable to the Milky Way's, but formed stars nearly twice as efficiently as their lower mass counterparts. Their red color comes from dust, lots of it. Dust forms from heavy elements produced by stellar nucleosynthesis, meaning these galaxies had already experienced multiple generations of stars by the time Webb observed them. High star formation efficiency is unexpected because the processes that convert gas into stars typically waste most of the available material. In modern galaxies, only about 10% of available gas actually becomes stars. The rest is heated by stellar radiation, dispersed by supernova explosions, or remains unconsolidated. Yet the red monsters appear to have achieved nearly 100% efficiency during their peak formation period. This might relate to the conditions in their dark matter halos. In the Lambda-CDM model, galaxies form within halos of dark matter that provide gravitational scaffolding. Gas falls into these halos, cools, and concentrates toward the center where it forms stars. The efficiency of this process depends on how quickly gas can cool and how effectively it can shed angular momentum to spiral inward rather than forming a stable disk. Perhaps certain dark matter halos in the early universe had properties that made them exceptionally efficient at star formation. Configurations that arose from the specific distribution of density fluctuations in the primordial universe, but became rare as cosmic structure evolved. These special environments would have been temporary, existing only during a narrow window of cosmic time before mergers and interactions disrupted their favorable conditions. The discovery of over 1,600 disk galaxies in the early universe challenges another assumption. Disks require coherent rotation, most of the galaxy's angular momentum pointing in the same direction so that gas and stars orbit in a flattened plane. In a chaotic young universe filled with mergers, you'd expect angular momentum to be randomized, producing elliptical galaxies rather than ordered disks. Yet there they are. Spiral galaxies with well-defined rotation curves existing when the universe was just 3 to 4 billion years old. The Big Wheel galaxy pushes this even further. displaying clear spiral arms within the first 2 billion years. These structures suggest that not all galaxy formation proceeded through the merger-dominated pathway cosmologists expected. Perhaps some regions of the early universe were less dense or had velocity structures that minimized disruptive encounters. Galaxies forming in these relatively quiet neighborhoods could build up mass through steady accretion rather than violent mergers, maintaining coherent rotation throughout their assembly. As the universe evolved and emptied out, such quiet regions became more common, explaining why disk galaxies eventually dominated. The turbulence observed in early galaxies offers another clue. When astronomers analyzed the gas kinematics in over 250 galaxies from the universe's first billion years, they found chaotic, clumpy structures rather than smooth rotating disks. Gas moved at high velocities in seemingly random directions. Dense clumps of star formation appeared scattered throughout these galaxies, rather than concentrated in spiral arms or central bulges. This turbulence might actually be the key to understanding rapid early star formation. In a smooth disk, gas orbits stably, and only slowly loses angular momentum to spiral inward. But in a turbulent, clumpy galaxy, gravitational instabilities can drive gas toward the center much more efficiently. Dense clumps lose energy through interactions with other clumps and with the galaxy's overall gravitational field, causing them to sink rapidly inward where they can form stars. As galaxies grew more massive and their rotation became more organized, this turbulent phase would have ended. The transition from clumpy, chaotic protogalaxies to ordered rotating disks might represent a critical moment in galaxy evolution, a phase change where gravitational dynamics shifted from turbulence-dominated to rotation-dominated. Webb's observations are capturing galaxies at various stages of this transition, giving us our first detailed view of how cosmic structure emerged from primordial chaos. The Reionization mystery deepens when we examine JADES GS Z13-1, the galaxy showing bright Lyman alpha emission just 330 million years after the Big Bang. Lyman alpha photons are ultraviolet light emitted when electrons in hydrogen atoms drop from the second energy level to the ground state. In a universe filled with neutral hydrogen, these photons should be absorbed almost immediately. They can't travel far through the neutral gas that supposedly pervaded the early universe. Yet we see them clearly. Either the neutral hydrogen fog wasn't as thick as models predicted, or it had already cleared in regions surrounding this galaxy. Both possibilities have profound implications for understanding reionization, the process by which the universe transitioned from neutral to ionized hydrogen. Standard reionization models suggest this process occurred gradually between 150 million and 1 billion years after the Big Bang, driven by ultraviolet radiation from the first stars and galaxies. But if galaxies like JADES-GS-Z 13-1 had already cleared out bubbles of ionized hydrogen by 330 million years, reionization must have begun earlier or proceeded faster than expected. Perhaps the first stars were more numerous or more luminous than models allow. Or perhaps additional ionizing sources existed. Early black holes, for instance, or exotic processes we haven't yet considered. The spectroscopic confirmation process continues. Webb's NIR-SPEC instrument can analyze individual galaxies in exquisite detail, measuring not just their distances, but their chemical compositions, star formation histories, and internal kinematics. Each new spectrum adds another piece to the puzzle, gradually building a comprehensive picture of how galaxies assembled in the cosmic dawn. Some early candidates have been confirmed as genuine high redshift galaxies with the properties initially estimated. Others turned out to be foreground interlopers, closer galaxies whose light mimicked the signatures of more distant objects. Still others revealed unexpected characteristics that don't fit neatly into existing categories, suggesting we're encountering types of cosmic structures that have no analogues in the modern universe. What's emerging is a picture of the early universe as a place of extraordinary diversity. Rather than a simple progression from small to large, from chaotic to ordered, galaxy formation followed multiple paths simultaneously. Some galaxies grew through mergers, others through steady accretion. Some formed stars in violent bursts, others more continuously. Some hosted rapidly growing black holes, others remained dominated by stellar populations. The specific path any given galaxy followed depended on its environment, its dark matter halo properties, and perhaps quantum fluctuations in the primordial density field that we can never directly observe. This complexity is actually reassuring. It suggests the Lambda-CDM model's basic framework remains sound. Dark matter provides gravitational scaffolding, cosmic expansion stretches structure from quantum seeds, baryonic physics converts gas into stars. But the details of how these processes played out in the universe's first billion years were far richer than simplified models captured. The bursty star formation hypothesis offers one compelling resolution. Computer simulations modeling the early universe suggest stars didn't form in the steady, continuous manner we observe in modern galaxies. Instead, they emerged in violent pulses, intense episodes of star birth, followed by long periods of dormancy. The mechanism works like this. Gas clouds collapse under gravity, igniting stellar fusion. These newborn stars flood their surroundings with ultraviolet radiation and stellar winds, pushing unconsumed gas away. When massive stars explode as supernovae after just a few million years, they inject enormous energy into the surrounding medium, driving gas even farther from the galaxy's center. For millions of years, star formation ceases entirely as the galaxy waits for gravity to slowly pull the expelled gas back inward. Then, the cycle repeats. Another burst of star formation, another expulsion, another dormant phase. This rhythmic pattern would make early galaxies appear far brighter during their active phases than their average stellar mass would suggest. If Webb happens to observe a galaxy during one of these bursts, it sees hundreds of brilliant young stars blazing away, dominating the light output. The galaxy looks massive because it's exceptionally bright, but much of that brightness comes from a temporary stellar fireworks display rather than from a huge accumulated population of stars. As the universe aged and galaxies grew larger, their gravitational pull became too strong for supernovae to expel gas effectively. The bursty pattern faded, replaced by the steady star formation we observe in mature galaxies today. Supercomputer simulations testing this hypothesis produce galaxies that match Webb's observations remarkably well. During burst phases, simulated galaxies briefly achieve star formation rates hundreds of times higher than the Milky Way's current rate, converting gas into stars with efficiencies approaching the theoretical maximum. Between bursts, they nearly vanish from view, dim enough to escape detection by even Webb's sensitive instruments. The galaxies we're seeing might represent the lucky ones caught mid-burst. while dozens or hundreds of their dormant cousins hide in the cosmic background, too faint to notice. But not every puzzle piece fits this explanation. The little red dots discovered in Webb's deep fields represent something entirely different. These peculiar objects are compact, extremely red, and far too bright for their apparent size. Initial photometric analysis suggested they were small, distant galaxies. Spectroscopic follow-up revealed the truth. They're supermassive black holes, many weighing millions or even billions of solar masses, actively feeding on surrounding gas just a few 100 million years after the Big Bang. How did black holes grow so massive so quickly? In the modern universe, supermassive black holes sit at the centers of most large galaxies, having accumulated mass over billions of years through steady accretion and occasional mergers. But these early giants had less than 500 million years to reach masses that took their modern counterparts cosmic ages to achieve. Either they started from unusually massive seeds, perhaps the remnants of the very first population 3 stars, or they accreted matter at rates far exceeding what current models allow. The accretion rate problem is substantial. When matter falls into a black hole, friction in the swirling accretion disk heats the material to millions of degrees, causing it to emit intense radiation. This radiation exerts outward pressure on surrounding gas, counteracting gravity's inward pull. The balance between gravity and radiation pressure sets a maximum accretion rate called the Eddington limit. Black holes feeding at this limit can roughly double their mass every few tens of millions of years. But to reach billions of solar masses by 500 million years after the Big Bang, starting from a stellar mass seed of perhaps 100 solar masses, requires sustained super-Eddington accretion, feeding faster than physics supposedly allows, unless the physics is more flexible than we thought. Recent theoretical work suggests early black holes might have exploited conditions unique to the primordial universe. The gas falling into these black holes was nearly pure hydrogen and helium, lacking the heavier elements that contribute to cooling in modern accretion disks. This pristine composition could alter the radiation pressure dynamics, potentially allowing higher accretion rates. Additionally, if these black holes formed from direct collapse rather than from stellar remnants, if massive gas clouds collapse directly into black holes without ever forming stars, they might have started with seeds of 10,000 or even 100,000 solar masses, dramatically shortening the time needed to reach supermassive scales. The abundance of these early supermassive black holes carries implications beyond galaxy formation. Black hole growth and galaxy growth appear intimately connected in the modern universe. The mass of a galaxy's central black hole correlates tightly with the mass of its stellar bulge. This relationship suggests black holes and their host galaxies co-evolve, each influencing the other's development. If supermassive black holes existed before their host galaxies fully assembled, the causal relationship might run backward in the early universe. Perhaps black holes formed first, and their intense radiation helped trigger or regulate the subsequent formation of stellar populations around them. The discovery of over 1,000 disk galaxies in the early universe presents a different kind of challenge. Disk galaxies, flat, rotating structures like the Milky Way, are fragile. They require stable, ordered rotation to maintain their characteristic spiral structure. In the early universe's crowded conditions, frequent galaxy mergers should have disrupted these delicate disks, producing irregular morphologies instead. Yet Webb finds disk galaxies already well established when the universe was just a few billion years old, accounting for roughly 40% of all galaxies at those epochs. A fraction far higher than models predicted. The Big Wheel galaxy exemplifies this mystery perfectly. Observed as it appeared less than 2 billion years after the Big Bang, it displays a clear spiral structure, complete with defined arms and a central bulge. Its very existence seems improbable. Spiral arms form from density waves propagating through a galactic disk, regions where stellar and gas density temporarily increases, triggering star formation that makes the arms visible. These density waves require a stable, settled disk to persist. In a universe where violent merger events were supposedly common, how did such a delicate structure survive? One possibility involves the role of dark matter halos. Simulations suggest that if a galaxy forms within an unusually smooth, unperturbed dark matter halo, one that hasn't experienced recent major mergers, the baryonic matter settling into it might assemble into a disk rather than a spheroid. The early universe might have contained more of these pristine halos than expected, providing safe environments where disk galaxies could form and persist despite the general chaos surrounding them. The JWST 7329 galaxy presents yet another anomaly. Observed 11.5 billion years in the past, just 2 billion years after the Big Bang, it contains a stellar population already 1.5 billion years old, implying star formation began merely 500 million years after the Big Bang. More puzzling still, the galaxy appears quenched. It has exhausted or expelled its cold gas supply, shutting down star formation at least 1 billion years before Webb observed it. In the modern universe, quenching typically occurs when active galactic nuclei, the intense radiation from feeding supermassive black holes, heat or expel gas from their host galaxies. But this explanation requires both a supermassive black hole and a massive galaxy to have assembled extraordinarily early, then for the black hole to have grown active enough to quench star formation while the universe was still in its infancy. Every new Webb observation seems to push some aspect of galaxy formation to earlier times or higher efficiencies than models comfortably accommodate. The standard Lambda-CDM framework isn't broken. The cosmic microwave background, large-scale structure, and elemental abundances still match its predictions beautifully. But the detailed astrophysics of how gas turns into stars, how black holes grow, and how galaxies settle into their final forms clearly contains surprises we haven't yet incorporated into our models. Consider the star formation efficiency problem. In modern galaxies, only about 10% of available gas eventually converts to stars. The rest gets heated, expelled by stellar winds and supernovae, or remains in diffuse form that never reaches the densities required for star formation. This inefficiency is actually crucial for explaining why galaxies aren't far more massive than observed. If all available gas turned into stars, we'd see galaxies much larger than those that actually exist. Yet some early Webb galaxies appear to have achieved near 100% efficiency, converting essentially all their gas into stars. This extreme efficiency might be real, reflecting genuinely different conditions in the primordial universe. Or it might be an observational artifact. We might be systematically underestimating the total gas content of these early galaxies, making their star formation appear more efficient than it actually is. Measuring gas content at such extreme distances is difficult. We typically infer it indirectly from dust emission or from theoretical expectations, rather than detecting it directly. The chemical composition of these early galaxies offers another clue. The very first stars, formed from pristine hydrogen and helium, would have been massive, short-lived, and prone to exploding as supernovae that scattered newly forged heavy elements into the surrounding gas. Second-generation stars formed from this enriched material. Each stellar generation further increases the metallicity, the abundance of elements heavier than helium. By measuring the metallicity of distant galaxies through spectroscopy, we can infer how many generations of stars have already lived and died. Webb's spectra reveal that even galaxies observed just 500 million years after the Big Bang already show measurable metallicity. They're not pristine. Multiple generations of stars have already cycled through birth and death, enriching the interstellar medium with carbon, oxygen, nitrogen, and iron. This chemical enrichment must have occurred very rapidly, within the first few 100 million years of cosmic history. The speed of this enrichment suggests either that the first stars formed earlier than we thought, or that they enrich their surroundings more efficiently than models predict, perhaps because they were more numerous or more massive than standard theories allow. Population 3 stars, the hypothetical first generation formed from primordial gas, remain undetected. Theory predicts they should have been extremely massive, perhaps 100 to 1,000 times the Sun's mass, burning brilliantly hot and dying quickly in violent explosions. Their supernovae would have been spectacular, briefly outshining entire protogalaxies. But these exotic objects remain theoretical. We've never observed one directly. Webb might change that. Among the thousands of galaxies it's already detected, some might contain population 3 stars caught in the act of formation or explosion. Identifying them requires careful spectral analysis, looking for the distinctive signature of zero metallicity stellar populations. Several candidate objects are under investigation, though confirmation remains elusive. If verified, detecting population 3 stars would represent one of astronomy's holy grails: direct observation of the very first stellar generation, the cosmic ancestors of every star that followed. The implications extend beyond academic curiosity. Understanding when and how the first stars formed directly impacts our knowledge of when life could first emerge in the universe. Stars create the heavy elements: carbon, oxygen, nitrogen, phosphorus, essential for chemistry complex enough to support biology. Before stellar nucleosynthesis enriched the cosmos with these elements, life as we know it couldn't exist. The faster metallicity built up, the earlier habitable environments could emerge. If disk galaxies stabilized earlier than expected, they might have provided stable environments for planetary systems to form and evolve sooner than previously thought possible. Our existence in a disk galaxy has always suggested these structures might be particularly favorable for life. Their settled rotation, regulated star formation, and relative stability could provide the long-term constancy needed for biological evolution. Finding abundant disk galaxies, already established just a few billion years after the Big Bang, suggests the cosmic conditions suitable for life might have emerged far earlier in cosmic history than we realized. The ongoing Webb investigation continues to refine our understanding. Each new observation adds data points, constraining theoretical models and revealing which predictions hold up and which require revision. The telescope's spectroscopic capabilities allow astronomers to measure not just light intensity, but its precise wavelength distribution, creating detailed chemical fingerprints of distant objects. This technique reveals composition, temperature, velocity, and physical conditions within galaxies billions of light-years away. When Webb's spectrograph splits ancient starlight into its constituent wavelengths, patterns emerge that tell stories about stellar populations, gas dynamics, and the progression of cosmic chemical enrichment through successive stellar generations. Some early galaxies display unexpected spectral features. JD's GS Z13W1, observed just 330 million years after the Big Bang, exhibits bright Lyman alpha emission, a specific wavelength of ultraviolet light emitted by hydrogen. This seems unremarkable until you consider the cosmic context. The early universe was filled with neutral hydrogen gas, a dense fog that should have absorbed Lyman alpha photons before they could escape their host galaxies. Astronomers had never detected this emission line earlier than 550 million years after the Big Bang. Yet here, it blazes clearly from a galaxy existing 220 million years before that theoretical limit. This observation challenges our understanding of reionization, the epoch when radiation from early stars and galaxies ionized the neutral hydrogen pervading space, clearing the cosmic fog. Standard models suggested this process completed roughly 1 billion years after the Big Bang, gradually transforming the universe from opaque to transparent. The clear Lyman alpha signal from JD's GS Z13W1 suggests the fog had already lifted in some regions far earlier than expected, creating transparent bubbles in the otherwise opaque early cosmos. How could this happen? Perhaps the first stars formed even earlier than current models predict, beginning reionization sooner. Or maybe early galaxies were more efficient at ionizing their surroundings than we realized, creating larger cleared regions faster. Some researchers propose that reionization wasn't a uniform process gradually sweeping across the universe, but rather a patchy, heterogeneous transformation, with some regions clearing while others remained foggy for extended periods. The galaxy might simply exist in an early cleared bubble, an ionized island in a neutral sea. This heterogeneous reionization scenario gains support from other Webb observations. Different sightlines through the early universe show varying degrees of neutral hydrogen absorption, suggesting a complex, uneven transformation rather than a smooth, universal process. Mapping this patchwork provides clues about the distribution of early galaxies and the efficiency with which they ionize their environments. The implications extend beyond academic curiosity. Reionization fundamentally changed the universe's character, making it transparent to ultraviolet and visible light, enabling galaxies to shine clearly across cosmic distances. Understanding when and how this happened affects our interpretation of essentially every observation of the early universe. If reionization proceeded differently than models predict, we may be systematically misinterpreting what we see in Webb's deep fields. Another spectroscopic surprise involves what astronomers call the little red dots. Compact, intensely red objects that initially appeared to be extraordinarily massive early galaxies. Follow-up spectroscopy revealed their true nature: supermassive black holes rapidly consuming gas, their feeding frenzies generating enormous luminosity. The friction of infalling material, heated to millions of degrees, emits intense radiation across the spectrum. Dust surrounding these active black holes absorbs ultraviolet light and re-emits it at longer, redder wavelengths, creating the distinctive crimson appearance. These objects aren't galaxies at all in the traditional sense. They're quasars, among the universe's most energetic phenomena, powered by black holes millions or billions of times the Sun's mass. Finding them so early raises profound questions. How did black holes grow so massive so quickly? Standard growth models suggest it takes hundreds of millions of years for black holes to accumulate such enormous masses through gradual accretion. Yet these objects exist when the universe was barely 500 million years old. One possibility involves black hole seeds. Perhaps the first black holes formed larger than we thought, starting with hundreds or thousands of solar masses, rather than the tens of solar masses produced by stellar collapse. These heavy seeds could grow to supermassive scales more rapidly. Alternatively, early black holes might have accreted matter far more efficiently than their modern counterparts, feeding at rates approaching or exceeding theoretical limits. Some models propose periods of super-Eddington accretion, where black holes temporarily exceed the maximum growth rate normally allowed by radiation pressure. The presence of these active black holes complicates interpreting early galaxy observations. When assessing a distant object's mass from its brightness, astronomers typically assume the light comes from stars. But if a significant fraction of luminosity originates from an actively feeding black hole, mass estimates become dramatically inflated. Some galaxies initially thought to challenge cosmological models turned out to be less massive than they appeared, their brightness amplified by central black holes rather than vast stellar populations. Distinguishing between starlight and black hole emission requires careful spectroscopic analysis. Stars produce relatively smooth spectra with absorption lines from elements in their atmospheres. Active black holes generate spectra with broad emission lines from rapidly moving gas near the event horizon, along with a distinct continuum shape from the accretion disk. Webb spectrographs can detect these subtle differences, allowing astronomers to decompose the total light into contributions from stars versus active galactic nuclei. This detective work continues across Webb's growing catalogue of early universe observations. For every mystery solved, new questions emerge. Galaxy J WST 7329 exemplifies this pattern. Located 11.5 billion light-years away, it appears as it existed just 2 billion years after the Big Bang. Spectroscopic analysis reveals a stellar population already 1.5 billion years old, stars that formed when the universe was merely 500 million years old. More remarkably, the galaxy appears quenched, having ceased star formation at least 1 billion years before we observe it. Quenching typically occurs in massive galaxies that have depleted their cold gas reservoirs, or where feedback from star formation or active black holes has heated or expelled the gas needed to form new stars. Finding a quenched galaxy, this early challenges models of galaxy evolution. Most simulations predict early galaxies should be actively forming stars, still growing rapidly through gas accretion and mergers. A galaxy that's already exhausted its fuel and shut down star formation represents a level of maturity seemingly incompatible with the universe's youth. The galaxy's stellar mass compounds the puzzle, roughly 4 times the Milky Way's total stellar content, despite existing when the universe was only 15% its current age. Building this much stellar mass requires prodigious star formation rates, sustained over hundreds of millions of years. Where did all that gas come from? How did it accumulate and convert to stars so efficiently? And what shut off the process so completely? These questions highlight the central tension emerging from Webb's observations. The early universe appears far more evolved, organized, and efficient at building complex structures than theoretical models anticipated. Galaxies grew bigger, faster. Stars formed more efficiently. Chemical enrichment proceeded more rapidly. Structures matured earlier. Each discovery individually might be accommodated within existing frameworks, but collectively, they suggest something fundamental about our models requires adjustment. Some astronomers propose revisions to star formation physics in the early universe. Perhaps the first stars were systematically more massive than modern stars, living shorter lives but producing heavier elements more rapidly. Or maybe star formation proceeded in intense bursts rather than the relatively steady pace observed in nearby galaxies, with periods of furious activity followed by quiescence, then renewed bursts. This bursty star formation could explain why some early galaxies appear so bright. We're catching them during peak bursts rather than average conditions. Computer simulations exploring this scenario show promising results. When models incorporate feedback from supernovae that periodically ejects gas from galaxies before gravity pulls it back for renewed star formation, the resulting galaxies exhibit rapid brightness variations. Observed during a burst, they appear far more luminous than their average state would suggest. This could reconcile some apparently overmassive galaxies with theoretical predictions without requiring fundamental changes to cosmology. Other researchers focus on dark matter's role. Standard models assume dark matter halos grow hierarchically through mergers, gradually building mass over cosmic time. Perhaps this process occurred faster than simulations predict, allowing larger halos to form earlier, providing the gravitational scaffolding for massive galaxies to assemble more rapidly. Alternatively, the relationship between dark matter, halo mass, and stellar mass might differ in the early universe, with stars forming more efficiently in a given halo mass than current models allow. These explanations avoid modifying fundamental cosmology, instead adjusting astrophysical processes within the standard Lambda-CDM framework. Most astronomers favor this approach, revising our understanding of how galaxies form rather than questioning the underlying cosmological model that successfully explains cosmic microwave background observations, large-scale structure, and the universe's expansion history. Yet some theorists explore more radical possibilities. What if the universe's expansion rate immediately after the Big Bang differed from current calculations? Faster early expansion could allow structures to form sooner, potentially explaining precociously massive galaxies. This would require new physics, perhaps additional forces or particles not included in standard models. Such modifications demand extraordinary evidence, but Webb's observations might eventually provide it. The red monsters illustrate another dimension of this puzzle. 3 massive galaxies identified at high redshift show stellar masses comparable to today's Milky Way, while existing just 1 to 2 billion years after the Big Bang. What distinguishes them is efficiency. They converted nearly twice as much available gas into stars compared to smaller contemporary galaxies. Typical galaxies convert roughly 10% of available gas into stars. These red monsters apparently achieved 20% efficiency or higher. Understanding why requires modeling the complex interplay between gas cooling, gravitational collapse, star formation, and feedback processes that regulate galaxy growth. Perhaps these particular galaxies experienced unusually low feedback, allowing gas to collapse and form stars without being disrupted by supernovae or stellar winds. Or they might have accreted gas more continuously, maintaining high star formation rates over extended periods. Their high dust content gives them the distinctive red appearance that inspired their nickname. Dust forms from heavy elements synthesized in stars and dispersed through supernovae. Abundant dust indicates substantial prior star formation and chemical enrichment. Further evidence these galaxies evolved rapidly. The dust absorbs ultraviolet starlight and re-emits it in infrared wavelengths, creating the red spectral signature Webb's instruments detect. Spectroscopic follow-up provides crucial context. By measuring emission and absorption lines, astronomers determine gas temperatures, densities, ionization states, and kinematics within these galaxies. This reveals whether gas is smoothly rotating, turbulently churning, or streaming inward to fuel ongoing star formation. Understanding the physical state of gas explains how efficiently it converts to stars, and why some galaxies excel at this process while others struggle. The Big Wheel galaxy adds another wrinkle. Discovered in early 2025, it displays clear spiral structure despite existing within the first 2 billion years after the Big Bang. Standard models predict early massive galaxies should be elliptical, smooth, featureless systems formed through violent mergers that destroyed any organized structure. Spiral galaxies require settled, rotating disks where density waves can organize stars and gas into elegant arms. This level of organization supposedly takes many billions of years to establish, yet here it sits, spiral structure already well developed at cosmic dawn. Either disk galaxies can form and stabilize far faster than models predict, or this particular galaxy followed an unusual evolutionary path. Perhaps it formed in an unusually quiescent environment, avoiding the disruptive mergers that typically destroy spiral structure in the early universe. Or maybe feedback from star formation and black hole activity somehow sculpted the gas into organized rotation more efficiently than standard processes allow. Each of these observations, the impossible light from JADES-GS-Z13-1, the little red dots masquerading as galaxies, the prematurely quenched JWST-7329, the hyper-efficient red monsters, the unexpectedly organized Big Wheel, individually challenges specific aspects of galaxy formation theory. Collectively, they paint a picture of an early universe more complex, more varied, and more efficient at building structure than decades of theoretical work anticipated. The pattern becomes clearer when you step back from individual objects and examine the entire population Webb has revealed. Over 1,000 disk galaxies resembling our Milky Way, populate regions of space where theory predicted they shouldn't exist. These aren't scattered anomalies. They represent roughly 42% of all galaxies Webb observed in certain epochs. Standard thinking assumed the cramped, chaotic early universe would tear apart any organized disk structure through frequent mergers and gravitational harassment. Yet there they sit, calmly rotating, their spiral arms and central bulges already well established. This discovery forces reconsideration of how quickly gravitational processes can organize matter. Disks require angular momentum, gas and stars orbiting a common center rather than moving randomly. They need time to shed chaotic motions through interactions and settle into ordered rotation. They benefit from periods of quiescence where major mergers don't disrupt delicate structures. The early universe supposedly provided none of these conditions. High galaxy densities meant frequent close encounters. Dark matter halos were still actively accreting mass, creating turbulent gravitational environments. Gas fractions were higher, making systems more responsive to perturbations. Perhaps the solution lies in recognizing different evolutionary pathways. Some galaxies might have formed in unusually isolated regions, cosmic backwaters where density happened to be lower. Others could have experienced early mergers that paradoxically created stable disks. If two gas-rich systems collided with aligned angular momentum, the resulting object might settle into rotation faster than a galaxy assembled through many small accretion events. The key is abandoning the assumption that all galaxies follow identical formation sequences. Spectroscopic observations reveal another crucial detail. Many early galaxies show signs of intense turbulence when astronomers measure gas velocities. Rather than smoothly rotating, the gas churns and swirls with velocity dispersions indicating chaotic motion. Over 250 galaxies analyzed from epochs 800 million to 1.5 billion years after the Big Bang display this characteristic. Their internal motions suggest gravitational instabilities, clumps of gas collapsing under their own weight, forming massive star clusters that then migrate through the galaxy, stirring up more turbulence through their gravitational influence. This turbulence affects star formation efficiency. In calm environments, gas clouds collapse, form stars, and the resulting stellar feedback, radiation pressure, stellar winds, supernovae, disrupts remaining gas, regulating how much can convert to stars. In turbulent systems, that regulation becomes less effective. Gas compresses more readily in shocks where turbulent flows collide. Gravitational instabilities create high-density regions that collapse rapidly. The result might be enhanced star formation rates compared to later, calmer epochs. But turbulence also explains why some early galaxies appear more massive than they actually are. When gas moves chaotically at high velocities, it mimics the gravitational signature of more mass. Astronomers measuring galaxy masses often rely on velocity dispersions. Faster motions indicate deeper gravitational potential wells, implying more mass. If turbulence contributes significantly to observed velocities, mass estimates will be inflated. Distinguishing between rotation, random thermal motion, and organized turbulence requires detailed spectroscopic mapping. Exactly what Webb's instruments enable. The bursty star formation scenario offers another resolution mechanism. Supercomputer simulations modeling early galaxy evolution reveal an oscillating pattern. Gas collapses under gravity, forming stars. Those stars, particularly massive ones, explode as supernovae within a few million years. The explosions heat remaining gas and drive powerful winds that blow it out of the galaxy's central regions. Star formation ceases. Over tens or hundreds of millions of years, gravity gradually pulls the expelled gas back. It cools, collapses, and the cycle repeats. This heartbeat creates dramatic variations in brightness. During active phases, galaxies blaze with newly formed massive stars, producing intense ultraviolet radiation. During quiescent phases, the massive stars have died, leaving behind longer-lived but dimmer, low-mass stars. If Webb happens to observe a galaxy during its bright phase, it appears more luminous and potentially more massive than its average state. This selection effect could explain why some early galaxies seem impossibly bright. We're catching them at peak luminosity. The model predicts specific observational signatures. Galaxies experiencing bursty star formation should show recent supernova remnants and superbubbles of hot gas. Their stellar populations should exhibit age spreads. Distinct generations of stars formed in separate bursts rather than continuous formation. Their chemical compositions should vary with radius, as later bursts use gas enriched by earlier stellar generations. Webb's spectroscopic capabilities can test these predictions, distinguishing genuinely massive galaxies from those temporarily brightened by bursty formation. Dark matter halos play a subtle role here. Standard Lambda-CDM cosmology assumes cold dark matter clumps hierarchically. Small halos form first, then merge to create progressively larger structures. Galaxies supposedly grow inside these halos, with their star formation regulated by how efficiently gas can cool and collapse within the dark matter potential well. Early epochs should feature numerous small halos hosting small galaxies, with massive halos rare because they haven't had time to assemble. Webb's observations challenge this timeline. Massive galaxies at high redshift require correspondingly massive dark matter halos to exist that early. Either halos assembled faster than models predict, or baryonic processes, ordinary matter physics, allowed galaxies to grow more massive than their dark matter halos would typically support. The latter possibility suggests feedback mechanisms were less effective early on, permitting higher fractions of available gas to convert into stars before being expelled. Some researchers propose modifications to dark matter properties themselves. If dark matter particles interact weakly with each other or with radiation in specific ways, halo assembly might proceed differently than cold dark matter assumes. Warm dark matter, for instance, would suppress small-scale structure formation while allowing large halos to grow earlier. Self-interacting dark matter could alter halo density profiles in ways that affect how efficiently gas cools and forms stars. These variations remain speculative, but demonstrate how Webb's observations might eventually constrain dark matter physics itself. Black holes provide yet another complication. The little red dots, compact objects that initially appeared to be massive galaxies, turned out to be something stranger. Their extreme brightness concentrated in tiny regions suggests supermassive black holes actively accreting gas. The accretion process converts gravitational potential energy into radiation with remarkable efficiency, producing luminosities that can outshine entire galaxies. A relatively small black hole consuming gas rapidly can mimic the brightness of billions of stars. Distinguishing black holes from stellar emission requires spectroscopy. Active galactic nuclei produce characteristic emission lines from highly ionized gas in the accretion disk and surrounding regions. The line ratios, comparing intensities of different elements and ionization states, reveal the energy source. Stellar radiation produces one pattern. Accretion onto black holes produces another. Webb's instruments can perform this diagnostic, separating genuine stellar mass from black hole-enhanced brightness. But the presence of supermassive black holes so early raises its own puzzle. These objects, with masses millions to billions of times the Sun, supposedly grow from stellar mass black hole seeds through accretion. That process has limits. The Eddington limit determines maximum accretion rates based on radiation pressure from the infalling material pushing back against gravity. growing a billion solar mass black hole from a stellar remnant in less than a billion years requires sustained accretion near the Eddington limit. It's possible but challenging to explain why so many early black holes apparently achieved this. Alternative formation channels might help. Instead of growing from stellar remnants, perhaps some supermassive black holes formed directly from massive gas clouds that collapsed without fragmenting into stars. These direct collapse black holes could start with masses thousands to tens of thousands of times the Sun, giving them a head start. Or maybe stellar mass black holes in dense early star clusters merged repeatedly, building up mass through gravitational wave-emitting collisions. Each scenario predicts different distributions of black hole masses and relationships to their host galaxies. Understanding which galaxies host active black holes matters for interpreting the overall population statistics. If many apparently massive early galaxies are actually lower mass systems with bright central black holes, the tension with Lambda-CDM cosmology eases considerably. The stellar masses become more consistent with theoretical predictions, and the rapid assembly problem diminishes. But this solution introduces new questions about black hole formation and growth in the early universe. Spectroscopic confirmation campaigns are ongoing. Webb's NIR-SPEC instrument can obtain detailed spectra for dozens of targets, measuring redshifts precisely and identifying emission line signatures. These observations distinguish photometric candidates, objects selected based on broadband colors that might be misidentified, from spectroscopically confirmed galaxies at specific redshifts. Early results show some candidates were indeed foreground objects or had incorrect redshift estimates. Others confirmed their extreme distances and unusual properties. The confirmed fraction matters enormously. If most candidates prove genuine, the challenge to existing models intensifies. If many turn out to be misidentifications or objects with inflated mass estimates, the problem shrinks to manageable proportions. Current data suggests something between these extremes. Real tensions exist, but not wholesale failures of cosmological theory. Roughly twice as many massive galaxies appear at high redshift as models comfortably predict. That's significant without being catastrophic. Fine-tuning may suffice. Adjusting parameters within existing frameworks, star formation efficiency, feedback strength, gas accretion rates, could potentially accommodate the observations. This wouldn't represent new physics, but rather better understanding of astrophysical processes within known physical laws. The challenge lies in making adjustments that explain early universe observations while preserving agreement with local universe properties. You can't simply dial up star formation efficiency for early galaxies without explaining why it decreased later. Population 3 stars represent another frontier Webb might illuminate. These hypothetical first-generation stars, formed from primordial gas containing only hydrogen and helium, would have been far more massive than typical stars today. Their lack of heavy elements meant less efficient cooling, requiring more mass to trigger gravitational collapse. Stars hundreds of times the Sun's mass might have been common, burning brilliantly but briefly before exploding as supernovae or collapsing into black holes. Detecting population 3 stars directly seems unlikely. They lived and died too quickly. But their influence might appear in other ways. The supermassive black holes they left behind could be the seeds that grew into the giants we observe. The heavy elements they synthesized and dispersed should appear in second-generation stars, creating distinctive chemical signatures. Some early galaxies might show unusually low metallicities, indicating they contain stars formed from gas only slightly enriched by population 3 supernovae. Webb's infrared capabilities make it uniquely suited to search for these signatures in the most distant, earliest galaxies. The implications extend beyond astrophysics into fundamental cosmology. If Lambda-CDM requires substantial modification to explain early galaxy populations, those modifications might affect predictions for other observables. The cosmic microwave background, large-scale structure, gravitational lensing statistics. Consistency across all these domains determines whether proposed solutions actually work or simply shift problems elsewhere. What becomes evident is that the early universe was more varied, more dynamic, and more efficient at building complex structures than decades of theoretical work anticipated. The challenges Webb presents aren't necessarily crises, but opportunities. Chances to refine understanding, discover new physics, and appreciate the richness of cosmic evolution during those formative first billion years. The profound lesson emerging from Webb's early observations isn't that our models are wrong. It's that the universe is far more inventive than we anticipated. The early cosmos wasn't a simple, orderly place where galaxies formed slowly and predictably. It was turbulent, chaotic, and remarkably efficient at creating complexity. Consider what this means for our understanding of cosmic time. We've long thought of galaxy evolution as a gradual process stretching across billions of years. Protogalaxies merge, accumulate gas, trigger star formation in measured bursts, slowly building toward the majestic spirals and ellipticals we observe today. But Webb shows us galaxies that accomplished in hundreds of millions of years what should have required billions. They didn't follow the script. The turbulence matters more than initially recognized. Detailed observations of early galaxies reveal chaotic internal motions, gas swirling violently, density variations creating clumps and voids, gravitational instabilities preventing smooth rotation. These aren't ordered systems. They're cosmic construction zones, messy and energetic. More than 250 young galaxies analyzed between 800 million and 1.5 billion years after the Big Bang show this pattern consistently. Most are turbulent, clumpy systems that haven't settled into the calm, rotating disks characteristic of mature galaxies. This turbulence might actually explain enhanced star formation efficiency. In chaotic environments, gas compression occurs more frequently and intensely. Colliding streams create density peaks that trigger star formation. Feedback from supernovae and stellar winds, rather than shutting down starbirth, might drive gas into denser regions where it forms stars more readily. The very messiness that seems inefficient could paradoxically boost efficiency. Then there's the big wheel galaxy, defying another expectation. Discovered in early 2025, this massive galaxy displays clear spiral structure despite existing within the first 2 billion years of cosmic history. You would expect early massive galaxies to be elliptical, smooth, featureless blobs resulting from violent mergers. Instead, Big Wheel shows organized spiral arms similar to the Milky Way today. Its existence suggests that ordered structures emerged earlier than thought possible, or that formation pathways we hadn't considered were operating in the young universe. The disk galaxy population adds another layer of surprise. Over 1,600 disk galaxies like our Milky Way appear in deep field observations spanning 9 to 13 billion years into the past. During those epochs, when the cosmos was cramped and dwarf galaxies swarmed, conventional wisdom held that tidal forces and frequent collisions would twist disk galaxies out of shape. They shouldn't survive intact, yet there they are, thousands of them, maintaining their structure against the odds. This has implications beyond astrophysics. If disk galaxies are common throughout cosmic history, and if such galaxies provide favorable environments for life, as our own existence suggests, then the window for biological evolution might open earlier than previously imagined. Habitable planets could have formed when the universe was only a few billion years old, giving life a much longer time frame to develop complexity and intelligence elsewhere in the cosmos. The Reionization picture grows more complicated with every observation. JADES GS Z13-1, appearing just 330 million years after the Big Bang, shows bright Lyman alpha emission that shouldn't be visible through the neutral hydrogen fog pervading that era. This emission line, never detected earlier than 550 million years previously, suggests the Reionization process wasn't uniform. Perhaps local ionized bubbles formed around particularly energetic galaxies, creating clear sight lines through the fog. Perhaps Reionization began earlier in some regions, proceeding in patches rather than sweeping uniformly across space. The spectroscopic confirmation campaigns continue revealing nuances. Some candidates prove to be foreground objects, misidentified by photometric analysis. Others confirm their extreme distances, but show lower masses than initial estimates suggested. Still others validate both distance and mass, cementing the challenge they pose. The confirmed fraction hovers around expectations. Enough tension to demand explanation, not enough to declare crisis. What emerges is a picture of cosmic diversity. The early universe wasn't a monolithic environment where all galaxies formed identically. Some regions experienced rapid assembly, others proceeded more slowly. Some galaxies converted gas into stars with remarkable efficiency. Others followed conventional patterns. Central black holes dominated certain systems, inflating their brightness. Bursty star formation characterized others, creating periodic luminosity spikes that catch our attention when we happen to observe during active phases. This diversity challenges simplified models, but enriches our understanding. The universe doesn't conform to neat categories. It explores possibilities, trying different formation pathways simultaneously. Dark matter halos collapse at varying rates depending on local density fluctuations. Gas accretion proceeds differently depending on environmental conditions. Feedback mechanisms operate with different intensities based on star formation history. All these variables combine to produce the observed variety. The little red dots exemplify this diversity. These compact, extremely red objects initially defied classification, too small to be typical galaxies, too bright to be ordinary active galactic nuclei. Spectroscopic analysis revealed them as massive black holes surrounded by dense gas and dust. Their red color comes from dust absorption, not redshift alone. They represent a phase of black hole growth we hadn't clearly identified before, perhaps the transition between initial seed formation and the fully developed quasars seen later. Black hole growth itself becomes a puzzle demanding solution. Supermassive black holes containing billions of solar masses appear surprisingly early. Growing from stellar mass seeds through gas accretion requires time, more time than available if you start from conventional mechanisms. Either the seeds were more massive than thought, perhaps remnants of population 3 stars weighing hundreds of solar masses, or accretion proceeded faster than standard theories allow, possibly through episodes of super Eddington growth where black holes consumed gas at rates exceeding theoretical limits. Population 3 stars remain tantalizingly beyond direct detection. These primordial giants, composed purely of hydrogen and helium, would have shone intensely but briefly before exploding or collapsing. Their direct light has long since faded, but their influence persists in chemical signatures imprinted on subsequent stellar generations and in the supermassive black holes they potentially seeded. Webb sensitivity might reveal extremely metal-poor stars in early galaxies, indicating gas enriched by just a few population 3 supernovae. Such discoveries would confirm theoretical predictions and illuminate conditions in the universe's first 100 million years. The cosmic timeline itself comes into sharper focus. The Dark Ages, stretching from recombination around 370,000 years to Reionization's onset perhaps 150 million years later, remain observationally inaccessible to optical and infrared telescopes. Only radio observations of neutral hydrogen's 21 centimeter emission might eventually probe this era. But the period immediately following, when first stars ignited and first galaxies assembled, now lies within Webb's grasp. Record-breaking distances continue falling. MOAM-Z14, confirmed at redshift 14.44, existed when the universe was barely 300 million years old, only 2% of its current age. Its light has traveled through expanding space for 13.5 billion years, showing us a galaxy forming when cosmic history had barely begun. That it's 100 times brighter than theoretical models predicted underscores the ongoing challenge. Yet the standard cosmological model hasn't collapsed. Lambda-CDM survives, battered but intact. The cosmic microwave background measurements, large-scale structure observations, nucleosynthesis abundances, all the other pillars supporting the model remain solid. What requires adjustment are astrophysical assumptions about galaxy formation efficiency, not fundamental cosmological parameters. This distinction matters enormously. Cosmology describes the universe's overall evolution, its expansion rate, composition, geometry. Astrophysics describes how matter behaves within that framework, how gas cools, how stars form, how feedback operates. You can modify astrophysical models substantially while leaving cosmology untouched. That's precisely what current observations demand. The fine-tuning needed isn't trivial. Star formation efficiency must increase in early epochs without violating physical constraints. Feedback mechanisms must permit rapid growth without suppressing it entirely. Gas accretion rates must accelerate beyond standard assumptions while remaining plausible. Each adjustment requires justification and must preserve agreement with later epoch observations where models already succeed. Multiple research teams approach the problem from different angles. Some focus on improving hydrodynamic simulations, incorporating physics previously neglected or oversimplified. Others analyze observational data more carefully, refining mass estimates and eliminating contaminants. Still others explore alternative formation scenarios, perhaps top-heavy initial mass functions producing more massive stars, or enhanced merger rates, concentrating mass faster than typical models allow. The bursty star formation hypothesis gains traction. Computer simulations incorporating detailed feedback physics show galaxies experiencing intense star formation episodes lasting millions of years, separated by quiet periods lasting tens of millions of years. During active phases, hundreds of stars form annually. During quiescent phases, formation nearly ceases. If we happen to observe during a burst, the galaxy appears much brighter than its average luminosity would suggest. This temporal variability complicates mass estimates. A galaxy caught during peak star formation looks more massive than it actually is if you assume steady star formation. Its brightness implies a certain stellar mass only if stars have been forming continuously. But if formation occurs in bursts, the current brightness might represent a temporary spike, and the true mass could be significantly lower. Environmental factors play underappreciated roles. Galaxy formation doesn't occur in isolation. Cosmic web filaments funnel gas toward dense nodes where galaxy clusters form. Proximity to other galaxies triggers mergers and interactions. Large-scale flows influenced by dark matter distribution affect gas availability. These environmental variations create the diversity we observe. What becomes clear is that early universe galaxy formation was messier, more varied, and more efficient than anticipated. The challenges Webb presents aren't necessarily failures of theory, but opportunities to refine understanding. Each surprising observation points toward physical processes operating differently than assumed, conditions varying more than expected, or phenomena occurring earlier than predicted. The search continues for increasingly distant galaxies. Webb's instruments can potentially detect objects at redshifts beyond 20, showing the universe when it was less than 200 million years old. Each new discovery pushes boundaries, revealing how quickly complexity emerged from the simple initial conditions following the Big Bang. And perhaps that's the deepest insight. Complexity arose rapidly. The universe didn't require billions of years to create interesting structures. Within a few 100 million years, massive galaxies assembled, stars formed in abundance, black holes grew to impressive sizes, and the cosmic landscape began resembling what we see today. The ingredients for life, heavy elements forged in stellar cores, appeared earlier than thought. The environment supporting planetary systems, stable galaxies with ongoing star formation, existed sooner than expected. We're witnessing not just distant galaxies, but alternative histories. Each object represents a different pathway through cosmic evolution, a different combination of circumstances producing different outcomes. Some galaxies grew rapidly through efficient star formation. Others accumulated mass through mergers. Some developed central black holes early. Others remained dominated by stellar processes longer. The universe, it turns out, is far more creative than our models imagined. It found ways to build galaxies faster than we thought possible, to organize matter more efficiently than we expected, to create complexity under conditions we assumed too chaotic. And it did this not through violating physical laws, but through exploring possibilities within those laws more thoroughly than our simplified models captured. That's what makes Webb's discoveries exciting rather than troubling. They don't break cosmology. They reveal how much we still have to learn about the universe's formative epochs. The framework remains sound, but the details need filling in, and those details promise to be far richer than anticipated. The galaxies appearing in Webb's first deep fields forced astronomers to reckon with a humbling truth. The early universe wasn't waiting patiently for billions of years to organize itself. It was already building empires, while our models predicted scattered villages. Every new observation sharpens the picture. Some of those impossibly bright early galaxies turned out to be black holes wearing stellar disguises. Others confirmed their masses, standing as genuine challenges requiring explanation. The bursty star formation hypothesis offers resolution for many cases. We're catching galaxies during temporary fireworks rather than steady burns. But not every mystery dissolves so neatly. JWST 7329 remains stubbornly anomalous. A galaxy that assembled 1.5 billion years worth of stars before the universe was 2 billion years old, then somehow quenched completely. The red monsters achieved star formation efficiencies that push theoretical limits. The big wheel displays spiral structure that shouldn't survive in the chaotic early cosmos. JADES-GS-Z 13-1 broadcasts Lyman alpha light through fog that should absorb it completely. What ties these discoveries together isn't that they break Lambda-CDM cosmology. The fundamental framework survives intact. Dark matter scaffolding, cosmic expansion, the Big Bang timeline all remain solid. What breaks are our comfortable assumptions about how galaxies form within that framework. We assumed star formation proceeded steadily. It actually pulsed in violent bursts. We assumed early galaxies would be small and messy. Many assembled into massive, organized structures remarkably quickly. We assumed Reionization swept uniformly across space. It apparently proceeded in complex patches. We assumed disk galaxies were fragile late bloomers. Over 1,000 of them appear fully formed in the young universe. The astrophysical processes governing how gas becomes stars, how black holes grow, how galaxies acquire structure, these operated differently, more efficiently, more rapidly than decades of modeling suggested, not impossibly, just faster and more varied than we anticipated. This distinction matters. If observations had violated cosmological predictions, wrong expansion rates, inconsistent element abundances, contradictory cosmic microwave background patterns that would signal fundamental problems requiring new physics. Instead, Webb reveals that we underestimated the efficiency and diversity of galaxy formation within an essentially correct cosmological model. The universe is teaching us that complexity emerges more readily than we thought. Give it dark matter halos, primordial gas, and a few 100 million years, and it will surprise you. Some regions will assemble massive galaxies through intense bursts of star formation. Others will grow massive black holes that dominate their surroundings. Some will organize into elegant spirals despite environmental chaos. Others will quench early, exhausting their fuel before cosmic noon. Population 3 stars remain tantalizingly beyond direct detection, but their influence appears everywhere. The chemical enrichment visible even in the earliest observed galaxies requires multiple stellar generations, supernovae dispersing heavy elements that enable subsequent star formation. Those first massive stars, burning briefly but brilliantly, seeded the universe with elements necessary for everything that followed. The disk galaxy population carries implications beyond astrophysics. If our own existence in a spiral galaxy suggests favorable conditions for life, finding thousands of similar systems already established when the universe was young opens fascinating possibilities. Habitable environments might have emerged billions of years earlier than previously imagined. Life could have started in galaxies that formed when our universe was in its infancy. spectroscopic confirmation continues revealing nuances. Some photometric candidates prove to be foreground interlopers. Others confirm their extreme distances, but show lower masses than initial estimates. Still others validate both distance and mass, cementing the puzzles they represent. The confirmed fraction settles around twice what models comfortably predict. Enough tension to demand explanation without requiring wholesale abandonment of existing theory. Multiple research teams attack the problem from different angles. Improved hydrodynamic simulations incorporate previously neglected physics. Refined observational techniques eliminate contaminants and sharpen mass estimates. Alternative formation scenarios explore whether top-heavy stellar populations or enhanced merger rates might explain rapid mass assembly. The bursty star formation mechanism gains support with each new simulation. Models incorporating detailed feedback physics naturally produce galaxies experiencing intense episodes separated by quiet periods. When caught during active phases, these galaxies appear extraordinarily bright, without requiring impossibly large stellar masses. The variability explains much of what initially seemed impossible. Black hole growth remains puzzling, but not necessarily contradictory. Heavy seed formation through direct collapse could provide massive starting points. Super Eddington accretion episodes might accelerate growth beyond standard rates. The little red dots, compact objects dominated by feeding black holes, might represent a formation phase we hadn't previously identified, a transition between initial seeds and fully developed quasars. Environmental factors deserve more attention. Galaxy formation doesn't occur in isolation. Cosmic web filaments funnel gas toward dense nodes. Proximity to neighbors triggers interactions. Large-scale flows affect gas availability. These variations create the diversity we observe. Different pathways producing different outcomes depending on local conditions. The turbulence observed in early galaxies might actually enhance efficiency. Chaotic gas motions create compression zones triggering star formation. Gravitational instabilities concentrate material. Feedback processes, rather than suppressing formation, drive gas into denser regions where it forms stars more readily. The messiness we see might be exactly what allowed rapid assembly. What emerges from all this is a picture of cosmic evolution, far richer than simplified models captured. The early universe wasn't a uniform environment where all galaxies followed identical formation sequences. It was diverse, dynamic, exploring multiple pathways simultaneously. Some galaxies grew through mergers. Others accumulated mass through steady accretion. Some converted gas into stars with remarkable efficiency. Others followed conventional patterns. Central black holes dominated certain systems. Bursty star formation characterized others. This diversity challenges neat categorization, but enriches understanding. The universe doesn't conform to simplified models. It tries different approaches, explores possibilities, creates variety within physical constraints. Dark matter halos collapse at varying rates. Gas accretion proceeds differently depending on environment. Feedback operates with different intensities based on formation history. These variables combine, producing the observed richness. The ongoing investigation continues pushing boundaries. Webb's instruments can potentially detect galaxies at redshifts beyond 20, showing the universe when it was less than 200 million years old. Each discovery illuminates conditions during those formative epochs, revealing how quickly complexity emerged from simple initial conditions. Record distances keep falling. galaxies appear at epochs once thought observationally inaccessible. Their existence, their masses, their structures all inform theoretical models, forcing refinements and adjustments. The conversation between observation and theory drives progress, each new data point constraining possibilities and pointing towards solutions. The search for population 3 signatures continues. These primordial giants left their mark in chemical abundance patterns, supermassive black hole seeds, and the rapidity of early enrichment. Webb sensitivity might reveal extremely metal-poor stars, indicating minimal prior enrichment. Such discoveries would confirm predictions and illuminate the universe's first 100 million years. Fine-tuning existing models appears sufficient. Star formation efficiency adjustments, feedback mechanism refinements, gas accretion rate modifications. These can accommodate observations without requiring new fundamental physics. The challenge lies in making adjustments that explain early epochs while preserving agreement with later times when models already succeed. Lambda-CDM survives this test. The cosmic microwave background, large-scale structure, nucleosynthesis abundances, all the other pillars supporting the model remain solid. What requires adjustment are astrophysical assumptions about galaxy formation efficiency, not cosmological parameters describing universal expansion and composition. This distinction provides reassurance. Cosmology itself isn't broken. The framework describing cosmic evolution remains sound. What needs refinement is understanding of how matter behaves within that framework, how gas cools, how stars form, how feedback operates. These are complicated processes involving turbulence, magnetic fields, radiation transport, chemical evolution, all difficult to model from first principles. The universe's creativity exceeds our modeling capacity. It finds pathways we hadn't considered, achieves efficiencies we thought impossible, creates structures we expected to take longer. Not through violating physics, but through exploring possibilities within physical laws more thoroughly than simplified models captured. That's the profound lesson. The early universe was messier, more violent, more efficient, and more varied than anticipated. Galaxies assembled faster, stars formed more readily. Black holes grew more rapidly, structures organized more quickly. Chemical enrichment proceeded more swiftly, all within the bounds of physics, but at the extreme edges of what those bounds allow. Webb's discoveries don't represent cosmological crisis, but astrophysical opportunity. Each surprising observation points toward physical processes operating differently than assumed, conditions varying more than expected, phenomena occurring earlier than predicted. Understanding these processes enriches our grasp of cosmic evolution. The implications extend beyond academic interest. If disk galaxies common throughout history provide favorable environments for life, and if heavy element enrichment occurred earlier than thought, then biological evolution might have begun when the universe was far younger. Civilizations could have arisen in galaxies that formed during cosmic dawn, giving them billions of years head start on humanity. We're witnessing not just distant galaxies, but cosmic history itself. Each photon reaching Webb's mirrors traveled through expanding space for over 13 billion years, carrying information encoded at emission. That information reveals conditions during epochs we can never visit, processes we can only infer, structures we can barely imagine. The universe at 300 million years old wasn't supposed to be interesting. It should have been dominated by small protogalaxies, messy clumps just beginning gravitational collapse. Instead, we find massive galaxies already assembled, stars forming prolifically, black holes growing to supermassive scales, structures organizing into coherent forms. This rapidity suggests something fundamental about how matter behaves under extreme conditions. The dense, hot, metal-poor environment of the early universe enabled processes that don't operate efficiently today. Perhaps top-heavy stellar populations produced more supernovae, more black holes, more enrichment. Perhaps gas dynamics worked differently when cosmic densities were higher. Perhaps feedback mechanisms that regulate modern star formation operated less effectively then. Understanding requires incorporating these early universe conditions into theoretical frameworks. Models developed to explain nearby galaxies might not apply directly to their distant ancestors. Different physics dominates different epochs. What works at redshift 0 might fail at redshift 10. The ongoing spectroscopic campaigns gradually separate genuine anomalies from misidentifications. Some apparently massive early galaxies reveal themselves as foreground objects. Others confirm their distances but show inflated brightness from central black holes. Still others validate both distance and mass, standing as real challenges demanding explanation. This winnowing process matters. Initial photometric observations cast wide nets, identifying candidates based on colors suggesting extreme distances. Spectroscopic follow-up confirms or refutes these identifications, measuring precise redshifts and analyzing emission lines that reveal physical conditions. The confirmed fraction determines whether observations represent minor adjustments to theory or major revisions. Current results suggest minor adjustments suffice. Roughly twice as many massive galaxies appear at high redshift as models predict, significant but not catastrophic. Bursty star formation, black hole contamination, and improved gas cooling efficiency can potentially explain this factor of 2 discrepancy without fundamentally altering cosmological frameworks. Yet each adjustment carries implications. Increase star formation efficiency in early epochs, and you must explain why it decreased later. Enhance black hole growth rates, and you need mechanisms producing heavy seeds or super Eddington accretion. Improve gas cooling, and you must identify what made early gas cool more efficiently than modern gas. These aren't insurmountable challenges. They're the normal process of scientific refinement, adjusting models to match observations, constraining parameters through data. Cosmology has weathered such adjustments before. Dark energy emerged from supernova observations, contradicting expectations. Dark matter arose from galaxy rotation curves, defying predictions. Each adjustment initially seemed radical, but ultimately strengthened the overall framework. Webb's observations likely follow this pattern. Initial shock gives way to refined understanding. Apparently impossible galaxies reveal themselves as extreme but explicable examples of known processes. Bursty formation, black hole contributions, environmental variations. These factors combine explaining observations without requiring revolutionary new physics. But even if no revolution materializes, the discoveries matter. They reveal cosmic evolution's richness, showing how varied and dynamic the early universe truly was. They illuminate epochs previously accessible only through theoretical extrapolation. They test models in regimes where they've never been tested before. And they remind us how much remains unknown, despite decades of increasingly sophisticated observations and ever more powerful simulations. The universe still surprises us. It still exceeds expectations, still reveals complexities we hadn't anticipated, still demonstrates that reality surpasses our capacity to fully model it. That's not failure. That's science working exactly as intended. Observations challenge theory. Theory adapts to observations. Understanding deepens. Questions multiply faster than answers, each solution revealing new puzzles, each discovery opening new frontiers. The early universe Webb reveals is stranger and more wonderful than we imagined. Not impossibly strange. Nothing violates known physics, but strange enough to demand better physics, more sophisticated models, deeper understanding. Strange enough to show that our comfortable theories, successful as they've been, remain incomplete. Galaxies formed faster than we thought. Stars blazed more brilliantly than we expected. Black holes grew more rapidly than we predicted. Structures organized more efficiently than we assumed. Chemical enrichment proceeded more swiftly than we imagined. All within the first billion years of cosmic history. That billion years, representing less than 10% of the universe's current age, witnessed transformations as profound as anything that followed. From nearly uniform primordial conditions to rich galactic ecosystems, from pure hydrogen and helium to metals enabling rocky planets, from dark silence to brilliant illumination, from simple to complex. Understanding those transformations matters because they set the stage for everything after. The galaxies Webb observes at cosmic dawn are ancestors of galaxies we see today. The processes operating then influenced evolution continuing now. The structures assembled early provided scaffolding for later development. We're piecing together cosmic history one observation at a time. Each spectrum adds detail. Each confirmed galaxy constrains models. Each surprising discovery points toward phenomena we need to understand better. The picture emerging isn't simple, isn't neat, isn't what we expected, but it's real, it's rich, and it's revealing the universe's actual history rather than the simplified version our models initially suggested. The James Webb Space Telescope has given us eyes to see farther than ever before. What we're seeing challenges assumptions, demands explanations, and promises deeper understanding, not through overturning established frameworks, but through revealing the complexity those frameworks contain. The early universe wasn't impossible. It was just more capable than we gave it credit for, more efficient at building structure, more varied in its pathways, more rapid in its evolution. And now, thanks to Webb, we're finally seeing it clearly enough to appreciate just how remarkable those first billion years truly were. The cosmos assembled itself faster and more cleverly than our theories anticipated, exploring possibilities within physical law more thoroughly than our models captured, creating complexity and beauty with a rapidity that continues surprising us. That's the real discovery. Not that our cosmology is wrong, but that the universe's creativity in working within that cosmology far exceeds what we imagined possible.